you have the slopes, and within that slopes, okay, nampak tu? Kena pakai. Okay, still boleh nampak. So within the slopes, you have this angle, right? So within these angles, you will notice that you have this amount of space. Sometimes in an area, okay, sometimes in an area, you don't have that luxury of space, especially in urban area. It doesn't matter urban area or even say in the remote area. The ones that I showed you, this is highway projects. This is from Seremban to KLIA. So within these highway projects, it's also in the remote area, but as you notice that once you have slopes, okay, you have to have that you have to comply with the requirements of that 6 meter, right? When you have that 6 meter, if your slopes is very high, so you have 10 berms of 60 meter, if it's just if it's just one straight line, you require just small amount of land. Okay, but based on the requirement, you need to have berms, right? You have slopes, you have berms, slope berms. So maximum of slope is actually just 6 meter. Then you have berms. So by having that, the requirements of the slopes is actually much longer. So the higher slope that it goes, you're actually losing lots of land, okay, because of this requirement of slope safety. So with this, people actually create this reinforced earth. Okay, with this reinforced earth, you can actually cut those parts of slopes and make it just vertical 90 degrees. So you don't have actually to comply with that requirements. Okay, so this is actually 2 tiers. So this is the first tier, this is on the second tier. So by having this, you can actually save lots of space. And in Penang, you can see lots of these things, definitely, because Penang don't have luxury of land, and land is very expensive in Penang Islands. Okay, in KL also, you're going to see lots of these things. In bridge embankments for flyover, okay, you can see at the bottom there. So you have lots of this. So this is what we call reinforced earth. So what you have in reinforced earth is actually, we have this layer of, this is the original slopes. You can see that it's very high. This is missionary. This is not person. This is missionary. This is lori hantu. No. Yes, this is lori hantu. I must English. So this is high. So this truck is not a small truck, it's very high. So if you can see this, you would be really scared to see that you have lots of soil at the back there that have this height of so-called failure of or very steep slopes. Okay, so in order to solve this, you can actually use reinforced earth. So soil, as you know that it's heavy. So when it's heavy in your retaining wall analysis, it's going to increase the amount of stress, right? Passive. Okay, so the active pressure. So what happens is that you replace it with sand. So this is sand, the backfill. So with the sand backfill, okay, so this one, sand is good in terms of permeability. So it doesn't hold to water. So it doesn't hold to water, they can just flush away all the water. And when that happens, you can actually you can actually don't have that risk of high active pressure actually develops at the back of your retaining walls. Okay, so you replace with this, but what you cannot see in your naked eyes is that each and every part of this you actually have the metal strips. Okay, So you have that metal strips. Within that metal strips, so this is the one that actually reinforce the earth, what we call mechanically stabilized earth or reinforced earth. Okay. Then you after that you put with the facings. Okay, so this is the face, this one at the back there. As you can see, this is actually for metal strips. So this is the metal strips. The metal strips, you can see that it's actually it has like those coagulants. Doctor, is the layer, sorry, they have process, doctor, is the layer with sands entirely or they are laid with aggregates and other size too like pressurites? Okay, so at the back here, basically we just use sand and it is lightly compacted. Is the linear with sand entirely or are they made with aggregates of other size? Yes. So this is, I believe that's a question. So this one at the back here, we just use sands. We just use clean sand. This is expensive, right? Yeah, use clean sand at the back here for drainage. Why we use clean sand? Why? Because I'm going to show to you that this is the metal strips. As you can see that in metal strips, you have that coagulated, okay? And throughout the strength for this, the reinforced earth is actually picked up by the frictions between these metal strips as well as the sand. So you can just imagine that when you use sand, each and every part of an area within this metal strip is in contact with that sand. Once you choose to change to crusher runs you have size 21 inch, 25, 38, 50, 75. Okay, when you have that size, you just take the smallest one. Say if you take 1 inch, 25. With that 25, you have the interlocking within that crusher runs. But what you lose out is actually the surface frictions between the crusher runs as well as this metal strips. So, which is why it is very important that we we like to maintain that uh, frictions because that is the main mechanisms that actually increase its stability. Okay, okay, good questions. So, and if you use crusher runs, the drainage is good, okay, but you will lose out on that frictions lah. Okay. In fact, even with the different types of sand, okay, different type of sands, you also going to have a different value of friction angles, right? When you have a different value of friction angles, you would notice that the strength or factor of safety of this going to reduce as you reduce the amount of friction angles within those sands. Because why? That frictions reduce, right? Frictions is very important. So that's why when you have a reductions of friction angles within the sands of the backfills, that is definitely going to reduce the amount of resistance that is provided to this metal strips. Okay. Okay. So these metal strips, you're going to bolt it to this one, this face, this here. Then it's just going to go at the back of this ball. Okay. So at the length of the design line. So the idea is actually you have, when you see a slopes, you have active zones and you have a resistant zones. Doesn't matter, this slopes like this, or it's 90 degrees. Okay, so you're going to have this active zone and resistance zones. So when you do mechanicalized stabilizer, can I just call RE? last time I also using a British terms, reinforced earth. Okay, so when you do the RE, reinforced earth, the idea is that you're going to extend these metal strips, the reinforcements, back to the resistance zones so that you can actually tie this thing to the resistance zones. Okay, mechanically stabilized earth or mechanically reinforced earth. Actually, I think it's a American terms. Last time Prof. Raziz likes that terms. Is the Americans graduates. Okay, so a steep slopes in a dry cohesive, cohesionless soil with a face inclined at beta. Okay, slopes to the horizontal where beta slopes greater than the internal frictions angles, okay, internal friction angles of the soil itself. Without the benefit of soil reinforcements, then the slopes will definitely collapse, right? Still remember, if you have a soil within the soil itself, you have the angles of internal shearing resistance, right? So within that angles, if you actually move much higher than that, then actually it starts to fail. Okay. And however, by the incorporates of stable soil reinforcement, the slopes may be rendered stable. Okay. Then investigations of the basic reinforcing mechanisms reveals that the soil in the slopes comprise of two distinctive zones, active zones and the resistance zones. Okay, so you have actually these two parts, these active zones, the one that wants to fill and the one that is resistance zones. So this is the resistance parts where you have those shear strengths. Okay, or if you have pile, so this area where you have need to consider the shear failure, right? Okay, so without reinforce the active zones is basically unstable and tend to move upwards and downwards with respect to the resistance zones. If the soil reinforcement is installed across the active and resistance zones, it can serve to stabilize the earth zones. The idea is that this is the active zones, okay? So this one is going to fail, actually tie back to the resistance zones, okay? A practical reinforcement layout would contain multiple layers of reinforcements with the length of LEJ, okay, this is active, embedded in the active zones, and length LEJ embedded in the resistance zones. We put E because you're going to see that E is actually meant for effective, okay? So this is in the resistance zones. The embedded length of LEJ should be sufficient enough to mobilize enough bond strengths, okay? Yes, frictions and those creaks within this resistance zone that you actually tie, okay? Yeah. Okay. Mobilize enough bonds. The embedded length of LEJ should be sufficient enough to mobilize enough bond strengths between the soil and the reinforcements to resist the disturbing force caused by active zones. As you know that in even natural conditions, these active zones wants to mobilize, wants to say it's going to fail. So, sorry. So that's why you actually tie it to the resistance zones. So this is the same concept that people use in soil nailing. Have you heard this word before? I believe Prof. Fauza should actually talks about soil nailing, maybe a little bit. So in soil nailings, even for the wood itself, basically you do in slopes. It's like you have a nail, then you hammer it to slopes. Okay. So then you do it at spacings, okay? Within this spacing, then when it's finished, it can be as it is. So meaning that the face of that slopes can be covered with uh, grass, or the face of the slopes they're going to spray a concrete shotcretes. Okay, so this is soil elements. It is actually they're going to drill inside the slopes, and when they drill inside the slopes, they're going to put a bar, a reinforcement bar. So before this, we are talking about reinforced earth. Reinforced earth, they are using the metal strips. In soil nailings, they are using a reinforcement bar. They use size 25 or 32 mm, okay? T-bar, 24 or 25 mm. Then they're going to drill maybe up to, say, 9 meter, or most that people are going to go is up to 12 meter, okay? So that is actually depends on the resistance zones. In hardly of design, I saw sometimes people go up to 50 meter, but most of the time people just do for 9 meter, okay? Those drillings. Let me show to you. I think video, yeah. Okay, so this is how they do swallowing. So first of all, they're going to actually the first of all, they actually going to create the hole, okay? They're going to drill. Then once they drill, then after that they're going to put a bar. Once they put a bar, then after that they're going to concrete, put the concrete inside the hole so that the bar can actually bond with the concrete. Okay? So when the bar is actually bond with the concrete, so inside here, then after that they're going to put that bar, okay, say T32 or T25 mm. So for 9 meter, they're going to put inside that, and after that they're going to use shotcretes. So they're going to pour the concrete using shotcretes. So they're going to shoot the concrete inside that. Then after that, with that they can actually create a one column, okay, one column of a concrete. With inside of concrete they have a bar. So this is what we call soil nail. The same concept as we use in the reinforced earth. Okay, the idea is that they want to do until it penetrates beyond the, or they want to actually means penetrates and holds at the resistance area. Okay, so within that it goes into the resistance zones, so you can actually ensure that the slope will not fail. Okay, so this is so the same concept. So for if you are dealing with rocks, they have different names. In rock they call rock dowel, but it's the same thing, the same machines. I'm going to show you. It's also the same machines. The only difference with rock dowel is that when you do analysis in rocks is like Lego. When rocks is like Lego, you have lots of discontinuity. You are actually you're going to do a geological mapping of that area. Then after that, I believe you already learned that in EAG 141, right? So you're going to know that which parts of the rock blocks. Then you're going to install this until the part that is in the sound rock. So in that case, is that you are actually nail the loose rock to the rock that is actually hard at the back there. Let me show to you in shortcuts. Okay, can you see the video? Okay, so this is, as you can see in here, the same machines. They are using the same machines, the same rebar. The only difference is actually just the analysis is going to be different, because for slopes you're going to do the slope analysis. For rocks you're going to calculate based on the kinematic stability of the rocks. Okay, so this is rocks. So once they do this, then they're going to put um, the bar. Then after that, they're going to concrete so that it holds there. Okay. The selection of concrete actually depends on the type of the bar for the saw nail as the rock towers, because sometimes you need to ensure that for the bar itself, is it either galvanized or not galvanized? It's galvanized, then you cannot simply just use any type of concrete mix. Those that have sometimes with a different mix, they're going to actually lose in terms of its frictions. Okay, yeah. This one is shotcretes. In shotcretes, basically, you already have that those bars, BRC bar within the surface. Okay, then once you already have that BRC bar within the surface, they just going to spray with the concretes. Okay, so this is shotcretes. Then once it's finished, you can see the whole slopes is full of concretes. so so that is shotcretes. I'm personally doesn't really like much on shotcretes, because when you have shotcretes, when you have shotcretes, the problem is that with shotcretes, as I showed to you in our first class, whenever that you have anything movement at the back there, if you have any scours, okay, this is concrete, it's not visible, right? Then everything is going to be washed away. Then you didn't notice at the back of that wall is actually already empty. Okay? So that's one problem. So when you have shotcretes, okay. So in soil nails, the finishing can be either with shotcretes, or naturally um, you have that grass throughout the whole slopes. Okay, and each of these blocks, you're going to see the concrete blocks at the heads of each soil nails. Okay, so the concepts they are using is actually the same concepts. So that it can actually hold it on the resistant zones. Okay, the same concept which we use for this reinforced earth. Okay, so far any questions? Okay, so in reinforced bond, okay, the length of the reinforced depends upon the bond characteristics, which in turn decide the load carrying capacity, and the length of reinforcement should be sufficient to prevent pull out of the resistance zone. Okay, as I mentioned before, we want to go up to the resistance zones, and we want to ensure that's sufficient so that it doesn't have that pull out. Okay, in assessing the bond performance for the design purpose, of purpose, the shear stress develops between soil and reinforcements are assumed to be uniformly distributed over the entire length, even though it is actually not uniform. Okay, so it is actually not uniform because of you have a different of over the pressure, and as I mentioned, if you use the sand that is not in high quality, then this is going to even have much more problems. Okay, you already lose out that bond. The shear stress is taken to be the product of vertical stress multiplied by the tangent, then the tangent delta, where the delta is the angle of the bond stress. Okay, for narrow rough strip reinforcements embedded in cohesionless field galaxy, If the field cause vertically affects stresses to the rest locally given rise to the enhanced pull-out resistance. Okay, so for narrow rough strips reinforcement embedded in cohesionless field, the latency is the field cause vertical affected stress to the rise locally given rise to the enhanced pull-out resistance. Okay, so can understand? Basically, the main idea is that you want to ensure that your strips have that pull-out resistance, right? So when it has a pull-out resistance, you need to ensure that that field of your backfill have enough amount of vertical loads, okay, that can actually hold these strips so that you can actually against that pull-out. Okay. Factor affecting tensile behavior of flexible reinforcements is the strength of reinforcing will reduce with passage of time. In case of metallic reinforcement, which is in practice galvanized steel, will be affected by the corrosion. Okay. Then it's either you want to choose either for galvanized steels or not galvanized steels. When you have a galvanized steels, you can actually reduce the corrosions rates. So when you reduce the corrosion rates, you can actually increase the service life of your designs. Okay, of the building that of the reinforced earth that you actually design. Okay, and cost reductions in tensile rupture loads. Therefore, the design strength to be considered in the strengths of the reinforcement available at the end of design life. The effects of corrosion in metallic reinforced taken into account by allowing prescribed sacrificial thickness which vary according to the design life. Okay, okay, so far any questions? Semua boleh faham tak? That is actually basics basics concepts. Okay, you have active zones, you have resistance zones. You want to put this one means dock at the resistance zones, and the main idea is that for it to get the bond for the pull-out resistance, although at the same time this is a materials. Okay, so this material is actually steels. Within the steels you have that corrosions. So if this steels is being galvanized, then you can actually reduce the amount of corrosion rates, which in turn can increase the service life. Okay, okay. The service life of a reinforced soil structure should be considered in design. In most applications, the selected design life of the reinforcing element is equal to the service life of the structure. So if the structure is designed for 100 years, then of course this reinforced earth has to be 100 years. If not, your building is stand there but you have a slope failure, then this thing going to fail as well. So it won't serve the purpose, right? So it must be a minimum of the structure itself. Okay? In certain cases, most foundations to embankment, the entire structure can have a long-term service life, but it may not be necessary for the enforced portion to function for a shorter time while the surrounding grounds gain strength. Okay, it is also possible that you can actually allow for ground attenuation so that it can actually gain strength within the time. But that is kind of rare since there's no actually an actual proof or scientifically proof of a long-term performance increments over any geotechnical structure that related to this reinforced earth. Okay, because even this one is just like about 40 years ago or 30 years ago. So there's actually no study or scientifically proven for that. But still maybe some theory textbook materials. Okay, so again, category. So this is temporary, years 1 to 2 years. Contractor site structure. You can also for short terms, 5 to 10 years, contractors like structural vessel reinforcement for short terms. Industry, 10 to 50 years, structure and mines. Long term, 60 years, marine structure, highway embankment, retaining walls. 20 years, highway retaining wall, highway structure, and bridge embankments. Okay, which is most of the time being used for this reinforced earth. Okay, so the design principles. The aim of design principles is to achieve an acceptable probability that design structure will perform satisfactorily during their intended life. Okay, with an appropriate degree of safety, they should sustain all loads and deformations of normal construction and use along with adequate durability and resistance to the effects of misuse or fire. Design or reinforced earth structure investigates two main criteria to develop the dimensions and layout of the reinforced earth structure. Okay, so this is the information that is very important: dimension as well as its layout. Okay, dimension is actually the external stability of reinforced soil wall is easily investigated since it behaves as rigid cavity structure and conform to the simple law of statics. Okay. Then analysis of internal stability is essentials one of designing enforcement against tension failure and ensuring that it has a sufficient anchorage length into the stable soil. Okay. So first of all, you need to consider its external failure mechanism. So it is same like a retaining wall that you already have learned before. Okay, you consider that this is one whole systems of that retaining wall. Okay, so external stability is considered reinforced structure as a whole and check stability for slidings, okay, overturning, bearing capacity failure, as well as slip failure. So the same like when you do for retaining wall. The only difference is actually for slip failure, right? For slip failure is basically you do for the slopes analysis. So within that slopes analysis, you need to ensure that, of course, this is not within the slip surface. So if it's within the slip surface, then if it fails, then everything will fail. Just imagine, initially you have very steep slopes with that high amount of volume, then if it fails, it's going to become like very catastrophic. So what we most concerns in reinforced earth is their internal failure mechanisms, okay, apart from the externals, okay. It covers mechanisms such as shear within the structure, okay, arrangement and behavior of reinforcement, and as well as backfill. It checks the stability for each reinforcement layer and stability of which within the reinforced fields, okay. So this is, you can see the tension failure, and this is the pull-out failure. So this is the two things that we need to consider. The tension failure is actually you're going to actually calculate the allowable tension in tie. Let me outside a little slow. This time, okay, there's metal, these metal strips. You're going to actually calculate each of that metal strips. You should actually just check by metal strips because all metal strips are using the same materials. All using the same materials. You just check one, then this is actually referring to all the same. Okay, so you're going to check the tension type, the levels, and as well as you want to check the effective length of your metal strips. The effective length meaning that it must actually pass through that reinforced zones. Okay, so this is actually two parts that you're going to check. So the first one is factor of safety against tie breakings. Okay, have you looked into your the notes? Have you downloaded this one? You can see that factor of safety against tie breaking, FOS, we have allowable tensions, okay, allowable tension in tie. So this is the metal strips, okay. We have F, steel ties yield strengths, okay. We have the width W is actually the width of these method strips. So we are talking about the width of these method strips, and you have T, the thickness of these method strips. Okay? Any questions? You faham eh? So it's just you dapat numbers, just put all the numbers inside this. So still strength, width, as well as thickness. Okay. Then after that, you want to calculate the maximum tensions. That's fine. Because FOS is actually based on the allowable tension within the tie over these maximum tensions of that source. Okay. So this is, you have two ways to calculate this. You can either use Rankine tie-back structure hypothesis or direct gravity structure hypothesis. So means two way for you to actually to calculate for this one. Okay. So the T next is gamma. This gamma is the gamma of the backfill. So the sand in the picture. So there, this gamma. Okay. You have height. This height is actually the height of the wall. Okay. So you see the wall. This is the height of that wall. You have Ka, active pressure, based on the backfill sand. So as you can see, active pressure is calculated based on the friction angle of the soil, right? So if you have a different amount of friction angle with the soil, then this going to have effects on the maximum tensions. As you can see in here, it has effects on the maximum tensions, then it also affect the factor of safety. If this number is high, meaning that this number is going to become low. If this number is low, this number going to become high. Okay. Then you have SH, then you have SV. S, it stands for spacing. Spacings, as I showed to you the picture, you can see this one. This is the spacings. If this is going to put like this, okay, so this is the vertical and this is going to be horizontal. So between this guy and this guy, this is horizontal spacing. This guy and this guy, this is the vertical spacing. Okay. So this is where you put the metal strips. And this is where you put the metal strips. So spacing. So that's why the most important is actually the dimension as well as the spacings. Okay. So horizontal spacing and vertical spacing of the metal strips. Okay. And this is active pressure. And this is coherent gravity methods. Okay. For coherent gravity methods, this is based on Rankine. This is based on coherent gravity methods. As you can see that if it's less than 6 meters, your height of the wall, you're going to use this one. So you have varies over the heights of the ZAC. Okay. But when it's more than 6 meters, just take a KA. Okay. So this is the K for corrugative methods. This is the K based on the Rankine tieback structure. Okay. So far, any questions? Just simply put all the numbers into a these parameters. So the correct gravity structure hypothesis, okay, maximum tension, so this Tmax, okay, you have gamma h, the height of your wall 32, the height of the wall, and the k based on the formula that I showed to you, or multiply by 1 times Ka and H, so SH and SV. So again, you can see that in here, H as well as SH and SV is the materials that you're actually playing around when you do your analysis and your design for tie breakings. Okay? Because you want to know what's the height of the wall that you can actually build, and once you do that, you're actually playing around with the spacing of that metal strips. The gamma as well as the Ka or K is basically based on the available material at sites. So you can assume the numbers that you usually use. But at the same time, see if you know that the site is within that, around that area, then it can actually estimates what type of sands that they actually available within that area. Then you can actually tweak to that an actual value of the friction angles as well as the gamma of the materials that you're going to use. So once you do the design, the things that you are actually playing around is these spacings. Okay, sometimes because the hitch is somehow it's already fixed, unless you have not yet fixed the height of your retaining wall that you want to play around. So that is actually the value that you actually okay. Okay, so this is how you're going to calculate factor of safety um, against the tie breakings. Okay, so this is one part. Another part is actually the required tie length. In the required tie length, okay, again, you have the spacing of vertical, you have spacing of horizontals, and you have the Ka, you have the factor of safety, and you have the two. This is the width of your strips, and then tangents. Okay, so based on the rankings, tie-back structure, and again you can actually use the what you call uh, the ranking tie-back structure hypothesis or correct gravity structure hypothesis. Okay. Okay. So ah yes, we already finished. So far, any questions? Okay, this one is it? Okay, this one it is actually the interactions, okay, and the interactions between uh, the wall as well as between the wall as well as the backfill. So it's not similar as the one that you use that 30, 35. Usually this value is about 10. You still remember when you do the retaining wall, you have that retaining wall is delta, right? So that value. So it is interactions between that concrete as well as the backfill. So usually the value that you use in this one is okay. So you can actually calculate based on ranking. Okay. For simplification, all strips can be considered. Yes, ranking always simplify things. So you can actually H naught over the Z means over the height. as you can see, okay, in here, so when the height is actually much deeper, right? So you just need like kind of shots when the height is much higher. So you actually need much longer, right? So guys, in required tile length, usually you need to use Excel to calculate it. So most of the time, I I would ask this in exam. Yes, even for this exam, because for exam normally you calculate in I had manual calculation, right? So manual calculations calculate for each height. So it's going to become quite difficult. So because usually you're going to use Excel for whenever that you have with Z, the height of the length. Okay, okay, so uh any questions? Okay, so
Doctor,
yep.
one more question, and I think it involves everybody here. So the question goes like this: will you appreciate our appreciation?
Sorry.
Will you appreciate our appreciation? Thank you, Doctor.
Yeah, thank you very much.
I think everyone can turn on the cameras.
Thank you guys.
Thank you, Doctor, for the amazing Sam.
Thank you, Doctor.
Thank you
Thank
very
you,
much.
doctor.
Thank you.
We look forward to seeing you in campus soon.
Yes, I miss you guys a lot. Okay. Ah, it's very nice. Thank you very much, guys. I really appreciate it.
Thank you, Doctor.
Thank you.
Love you, Doctor.
Okay. So I'm really happy to see you guys. Okay, so this is our last class. So if you have any questions after this, you can actually ask me. Okay.
All right, doctor.
Okay. So thank you very much, guys. Do you have any questions? So far, any questions? Okay. For